Hello students, welcome to the next lecture on the numerical analysis. Today we will describe the Gauss-Seidel method. I will explain you the two different methods for solving the same problem, and I consider the 10 examples so that you can understand it very well. Myself Dr. Harish Gar. You can simply follow my YouTube channel Dr. Harish Gar for finding the various lectures on the numerical analysis. So what we have discussed is, if you have the system of the equation as Ax is equal to b, how you can solve this system numerically, then we have discretized into the two categories. One is called as the direct method, second is called as the indirect method. It is also called as iterative methods. In the direct method we call as the Gauss elimination, Jordan, Kraut, Kolesky and so on. While in the iterative method we have described the Jacobi and the Gauss-Seidel. Now in this lecture I will teach you how you can solve the problems related to the Gauss-Seidel. While the Jacobi method we have already discussed in our last lecture, you can see there is a playlist of the numerical analysis, and there are the direct method of the Gauss eliminations, examples, MATLAB code. This is the Jacobi method we have described and the respective MATLAB codes in this playlist. You can simply follow that and you can watch them. Now what is the Gauss-Seidel method? First of all, it's an iterative method which are used for finding the approximate solution. Remember, it's not give you the exact solution. It will give you the approximate solution here. So what is the meaning of the approximation? You start with the initial approximation, let's say x of 0, and then based on this information you can find the new approximation. Based on this new approximation you can find the next new approximation, and so on until you will get your desired accuracy. Desired accuracy means you will get the error up to the 10 to the power minus 3, or you can say the error will be less than of 0.001, or you can say up to the 4 decimal places. As per on your choice, you can say your target will be achievable. So in this lecture I will teach you the two different methods for solving the system of equation using Gauss-Seidel method. The first method is, if you consider the system of the equation Ax is equal to b, which is represented as here, then whenever you want to apply the Gauss-Seidel method, or you can say the Jacobi method, these are two different methods. The first step is you need to check whether the matrix associated with this system is a diagonal dominant or not. What is the meaning of the diagonal dominant? If you look at the first row, the diagonal value is my A11. The absolute value of this A11 must be greater than of the remaining elements in that particular row. That's the meaning of this. Similarly, for the second row, A22 must be greater than of the remaining elements of this absolute value of this other element, and so on. If this is true for all these rows, then we can say it's a diagonal dominant. Now if the matrix A is the diagonal dominant, then you can find the value of the x1 from the first equation, x2 from the second equation, and xn from the last equation. For example, if you find the value of the x1 from this, you can get as b1 minus of this divided by a11. Similarly for the x2 and xn. Now how you can apply the Gauss-Seidel method to this? So we can start with the initial approximation, then I can substitute this x1, x2, xn in this equation, so that your target is to find the next approximation as x1. So basically your target is to find x1 dash, x21 and xn1. So how you can find the firstly of x11? So I can substitute all these previous value in the first equation because of the x1. Then I can get this value as here. I can substitute this value, you will get this new value of x1. Then how you can find the x2? I can substitute here, but you can see there is a present of the x1. So whether I have used this value as a new value, what is that? This is my new value, or I can use as the old value. Old value is my here, because we have the two different values. So if you are using the old value here, then the method is called as the Jacobi method that we discussed earlier, and if we use the new value, then we call as the Gauss-Seidel method. So what you can do now, you can see I can substitute here as a new value. This is the x3, but we are not calculated so far the new value of x3, so I can consider this is my old value, this is my old value. So that means I can use the new value of the x1 and the others are my previous values, and I can substitute in my second equation. I can get as here. Similarly, if you are using this x3, it will be my a33, it is my b3 minus a3x1 minus a3x2 minus a34x4 and so on. Now you can see again this is x1, so I can use this as a new value. x2 I already computed new value. x4 we are not computed, so this is my old value and so on. So based on that we can compute as a x3. Similarly I can substitute here which are the new values and the old values. So in general we can say this is the iterative method. Now if you look about this matrix, this is I minus 1. So what is that? This is nothing but my lower matrix, and this is I plus 1. This is my upper matrix. So because this is for the ith row, I called as this is the diagonal plus low. I can define the second method also. So what is that? I can break this matrix A into the three matrices called as the strictly lower, upper and the diagonals. I can substitute this value here. So as I described in the first method, it consists of the D plus L as a one pair. Then I can find the value of the X from here, which comes to be this. Or in terms of the iteration form, I can written this as xn plus 1. This is also the X, I can written like here. Now if I say this is the iterative scheme, so what is the general form of the iterative? Here you can compare them. This is the value of my H and this is the value of my C. So you can say the iterative scheme of the Gauss-Seidel method is my here, where H is my this is called as Gauss-Seidel iterative method. Fine. So once you can calculate the value of H and C, so your target is to find how you can find the H and C. For example, so now you have the two different methods. So which one gives you the condition for the convergent? The first one is if A is my diagonal dominant. If A is my diagonal dominant, then convergence is always. Remember, once you prove that the system is diagonal dominant, then it's convergent for any value of the x0. You can start the value of the x0 as 0, 0, 0. You can start the value of the x0 as 0.8 minus 0.3 or 7, or you can take the x0 as 1, 1, minus 1 or anything. On the other hand, if the matrix is not diagonal dominant, then we are not sure about the convergent. How we can make the sure of the convergence? We can find the spectral radius of the matrix H. What is the spectral radius? It is denoted by rho of the H. How you can find? We can find the eigenvalue of this matrix H, and then we can find the absolute value of this. If I prove that the spectral radius, that is the maximum eigenvalue of absolute value, is less than 1, then the convergence occur, otherwise not. For example, look at the one example. Check whether it's a diagonal dominant or not, or whether the Gauss-Seidel method applicable or not. So firstly we will check whether the matrix A is a diagonal dominant or not. Look at the first diagonal value 1. Absolute value of the 1, is it greater than of this? You can see this is not satisfied. Similarly you can check for the second one. The diagonal entry 1 is not greater than of this 1 plus 1. Similarly for this third one, it is not greater than. So it means this is not diagonal dominant. Can you convert this matrix? You can rearrange the rows. Can you rearrange the rows so that it satisfies this property? Again, it is not. For example, I can change R1 and R2. What will happen? Your first equation will be here, second equation will be here, third equation as such. Then again you can see 1 is not greater than of 1 plus 1. Fine. So it means it is not diagonal dominant. If you can interchange them and it is a diagonal dominant, then the Gauss-Seidel method applicable. So it means we are unable to rearrange, so the diagonal is not here. Then we are apply for the second method, that is a spectral radius. For that you need the value of the D plus L and the U. How you can find the value of U? U is my upper matrix of strictly upper. That means all these values are 0, and here you can find the value of the D plus L inverse, because this is the matrix. You can use your calculator and find it. Then I can multiply this D plus L and U as here. How you can find the eigenvalue of the H? We can start from here. I can substitute, what is the I? I is my identity matrix of 3 cross 3. So I can substitute value here, you will get this. Then You can expand this value, it's a minus of this and so on, you will get as here. Then what is the maximum value of this absolute? It's come to be 2. So the spectral radius is my 2. Fine. So your spectral radius 2, which is greater than 1, hence the Gauss-Seidel method will be divergence. So there is no need to solve this problem. You can always check whether the Gauss-Seidel method converges or not. If it is convergent, then we can find the solution. For example, here, perform the 3 iteration of the Gauss-Seidel method. So your first target, check whether it's satisfied or not. So 4 is greater than of 2 plus 1, satisfied. Second, 3 is greater than of 1 plus 1, again satisfied hand here. So it is a diagonal dominant. So once it's a diagonal dominant, it means the Gauss-Seidel method will convergent for any value of the initial approximation. In this question, it is given that you have to take this initial approximation. Once the Gauss-Seidel method is applicable, you can find the value of the x1 from the first equation, find the value of the x2 from the second, and x3 from the third. Then you can write in the iterative manner, like this is my n plus 1, this is the n and n. This is the n plus 1 because x1 is already computed, so I can written as n plus 1, and x3, x1 and here. Then your target is to complete this table. Fine. So your target always to complete this table. How? Look at that. I can firstly find the first value. This is the x1. I can use this value 1 over 4. 2 into x2. What is the x2 value is? 0.8 minus x3. Fine. So after the calculation, you will get as 0.4750. Then for the x2, I can substitute here. But this is the value of the x1. This is my new value. So I can substitute here 4 minus new value. 4 minus new value. X3, because there is no value of the x3 calculated so far, so I can use the previous value. So after the calculation, we can substitute this value as here. Then for the third case, I can substitute this. I already computed the x1, which is the new value, as 0.4750 minus 2 into x2, which is already computed, so I can substitute as here. So after the calculation, you will get this is it. Then for the second iteration, how you can find that? This is the x1, again come back on here. So 1 over 4 minus x2. So x2 is my here because this is the new updated value, 2.10083 minus x3. This is a new updated value. So this is 5931. So after the calculation, you will get as here. Similarly for this equation, I can use this one, x1. Now this is my x1, x3. This is my x3. So I can find this value here. For the equation x3, I can use this. x1 is my here, x2 is my here. So I can get this value. Similarly for the third equation, I can do like this. So since we need to perform the 3 equation only, so at the end of this, the right answers are x1, x2 and x3 are the solution. Let's see, we can perform the same question with the help of the second method as here. So your target is to find this. So what is the A? You can write A and B here. What is the D plus L? That is my, this value is my D plus L and U is my here. You can find the D plus L of inverse. That's a very simple. I can show you that you can firstly write the inverse of the diagonal, simply 1 by 6 here. Then the rest values as here. Then for the finding of the inverse, we can find the cofactor of this. It will be 6. So 6 divided by the diagonal entry. So it will be my 1 by 12 and so on, which comes to be here. Then I can find the value of the h. I can multiply the h by using here. I can multiply this by b vector. We can get as c. Otherwise, you can use your calculator. This method is useful for you only when you are using the calculator frequently. So I recommended you can use the calculator. So I can substitute the value of the h and c as here. You will get the iterative equation this. Again, your target is to complete this table. So what is that? You can save this matrix as a in your calculator. You can save this matrix as a b in your calculator and this value as your x. So I can substitute this value of x in your calculator you will get as 0.1, 0.8, 0.5. So after that multiply, you will get this complete answer as here. While in the first method we have to compute one by one, but if you are using this matrix method, all the values are computed at the same time. Then you can save this value as A, then this value in the calculator is saved as mat answer plus this value as B. Again you can press them, you can get 3 values as here. Similarly for this third. So this is the way you can get your answers in a simple. Look at this another one. Check whether it's a diagonal dominant or not. You can see 4 is greater than of the 1 plus 2, 5 is greater than of the 3 plus 1, and here. So now it's a diagonal dominant, so the Gauss-Seidel method will always converge for any initial guess. In this case, initial guess is my 0, 0, 0. Find the value of x1 from here, x2 from this, and x3 as here. Then we can write in the iterative equations, which is come to be here. This is n plus 1, x1, and so on. Your target is to complete this table. Let's start with 0. So what is the value of this? So it's a 1 over 4. 4 minus 0 minus 0. It is my 1. Fine. How you can substitute here? It is 1 over 5. 7 minus x1. x1 is a new value. x3, there is no new value, is a 0. So basically x3 is nothing but my z. So this is my x2 and x1. So this is my 0. So it is a 4 by 5.8 and so on. Similarly for this is here. Based on these new values, we can compute this value. We can get as 0.6 in here, like 1 over 4. x2 is my previous value. x3 is my previous value. So after the calculation, you will get this number as 0.6. Similarly for the others. We can perform the third equation as well, and at the end of the 3 iteration, you will get the approximate solution as here. If I compute this same method by the second method, again our target is to write the d plus l and the u. You can find the d plus l inverse. Firstly, you can write is easily as a diagonal entries. Fine. These values are my 0. This value is negative. Find the cofactor of this. It is 9. So 9 divided by the diagonal entries. 4 into 5 into 3. So it's a minus 3 over 20 and so on. Fine. Then you can find the value of the h and c as here. Substitute the value of the h and c in this case, you will get this as. Then your target is to compute this matrix. I can take the initial guess as 0, 0, 0. Then you will get as first one is 1.8.4. Then I can substitute this value as here, multiply this matrix and add with this, you will get these equations. So your required solution as my here. Always use your calculator so that you can get your answer within a fraction of a second. Look at this one. So is it a diagonal dominant? Yes, it's a diagonal dominant. So you can apply the Gauss-Seidel method. Now you can see if you apply the second method, then it is my 4 cross 4. Then it is difficult, you can apply for this calculator. So I can prefer the first method. I can find the x1 from here and so on. I can write in the iterative form, that is x and this method. Now since in this case it is not given that how many iterations you need to perform. So I can perform the iteration until I get the 4 decimal places match. If nothing is given to you, you can perform the experiments until the 4 decimal places will match. So let's start with the first one. I can substitute value of the 0, 0, 0. Fourth value is also 0 here. So 0, 0, 0, answer is 0.3. I can substitute here, it's a 1.5 plus, what is the x1? It's a new value, 0.3. x3, there is no new value, it's a 0, it's a 0. So the answer will be my 1.56 and so on. Substitute this new value in these equations, I can get these 4 new values as here. Now clearly says that up to the 4 decimal places they are not matched. So I can compute the next iteration 4th. Again you can see up to the 4 decimal places they are not matched. I can compute the 5th iteration. Again they are not matched. I can compute, this is up to the 3 decimal places they match. But we need at least 4 decimal places. So now you can see I can return 1 as 999 here. So the 5th, 6th and the 7th iterations are almost same. The right answer will be here. You can also check your answer whether this is a correct or not. You can substitute this value in the given Ax is equal to B, check whether this equation is satisfied or not. Look at this one. So again you can see this is a 3 cross 3, so you can apply the first method and the second method both at the same time. Clearly say this is the diagonal dominant because all these conditions satisfied. I can find the value of the x from the first case, y from the second, and the z from the third. I can write this equation in the form of the iterative like of this. Since the initial value is not given to you, you may take as a 0, 0, 0, or you may take 1, 1.3, or you can take any of the values as per your own convenience. Again, nothing is given to you how many decimal places you needed, so I can fit as up to the 4 decimal places. Can you find the first iteration easily? What is the answer of this first equation when 0 and 0? So it is my 10 divided by 3. If you substitute here, it is my 1 by 4, 6 minus x1 is a new value, mine plus z is no previous value, and which value is at here. Now based on this you can substitute again at here, you will get these new values here. Clearly says up to the 3 decimal or 4 decimal they are not matched, then we can compute the fourth value. Again you can see the fourth value is not matched with the third value. I can compute the fifth equation is not matched with them, and so on. Now you can see the fifth and the sixth are almost similar up to the 3 decimal places, but if you want the fourth decimal place, you can find the seventh equation. You will get the approximate solution as here. The seventh equation will give you the answer as 3, 1 and 1, and you can see 6 and 7 are almost similar, so you can get the solution as 3, 1, 1. Look at one more example. Again nothing is given to you, so we can do the calculation up to the 4 decimal places. Check whether it's a diagonal dominant. Clearly says that it's a diagonal dominant. Okay, make sure that if my equation will be like here, say 20 minus 2z is 44 and 10x plus 2y plus z is my 9, and the third equation is same. Fine student? Then you can see, is it a diagonal dominant? No. Why? Because the first equation is not greater than of this one. Fine. Then how you can proceed with them? So firstly, then you can rearrange the equation. Can you interchange the equation? If I interchange the first and second, it becomes my here. Is it the diagonal dominant? Yes. Then you can proceed. So make sure whenever you want to apply the Gauss-Seidel, it must satisfy. If it is not satisfied, then you can check the spectral radius. If the spectral radius of the H is less than 1, then you can proceed with this given matrix. Otherwise convergence is not guaranteed. We can find the x, y, z from here. We can write in a iterative manner this way. I can start with a 0, 0, 0. I can substitute here, the first value will be 0.9. I can substitute here, second value 44, x is my new value, 2 into this is 1.8 plus z, there is no previous value, so it's my 0. So after the calculation you will get as here. Now again you can substitute this value in this case, 9 minus y, the new value of the y is my 2.11, value of the z is my 1.747. After the calculation you get here. You substitute these values in the rest of the equation, you will get here. Clearly says up to the 4 decimal places they are not matched, then we can find the third equations and here. Similarly, you can see up to the third equation they are not matched, we can find the fourth equation. They are not matched up to the 4 decimal places, we can find the fifth decimal and same. Now clearly says the fourth and the fifth equations are same, so your required solution is this one is the right. So you have to perform the equation until you will get the right solution. You can solve the same question with the help of the second method as well, you will get the same as solution. Look at one more example. Is it a diagonal dominant? Yes, because 4 is greater than of the 1 plus 1 and here. So once it's here, initial solution is not given to you, you can start with the anyone. Find the value of the x from the first equation, y from the second and the z from the third. I can write this in terms of the iterative equation which comes to be this one. Then you can start from here. What is the value of this first one? Y is 0, z is 0, it is my 3. I can substitute here, this is my minus 1, x is the new value, z is the previous value. so it is my 0.5. I can substitute here 5, the value of the x is new, y is my new 1, so it is my 3 by 4, that's my 0.75. Fine. Then I can use this value, substitute here. So for example, I can substitute this plus y is my 0.5, minus z is my 0.75. So after the calculation you will get this answer. Thank you. Again, you can see the 4 decimal places are not matched. Then we can compute the third equations, and here see the third equation is not matched with the second equation. We can compute the fourth equation. Again the fourth equation is not matched. Then we can find the fifth equation, sixth equation, and seventh equation. Now you can see the seventh and the sixth are almost similar, so we can get the solution as 3, 1, 1. You can check this system. You can substitute in the given system ax is equal to b, check whether the left hand side and the right hand sides are equal or not. If they are not equal, then your answer is not correct, otherwise correct. So this is the way you can solve this Gauss-Seidel method in a very simple manner. So I will teach you the next lecture on the successive hour relaxation. Till then you can simply look at this playlist of the numerical analysis where the previous lecture Gauss-Seidel MATLAB code of the Gauss-Seidel is already explained. Till then you can simply like, share and comment on my videos. Best of luck students. Happy learning.